Thank you so much for having me. So these are my disclosures. I report prior employment by Roche. And this project, as part of my new role at Harvard Medical School, was supported by a contract with the FDA Sentinel Innovation Center. So as a background, I work mostly in the field of real-world evidence, and real-world evidence is getting an increasing role in complementing evidence coming from clinical trials. But of course, there are some limitations in terms of confounding and so on and so forth, and especially when working with electronic health records like I do in the field of oncology. One of the biggest issues we have is partially observed or missing data in variables that are quite important that we want to measure as potential confounding factors, and this can be labs vitals, lifestyle factors, and so on. And the reasons for the missingness is can be manifold and is often not really known. And so there are a couple of missing data taxonomies, such as missing data mechanisms according to Rubin, and missing data patterns such as monotone and non-monotone. And as I already mentioned, there are some unresolved challenges for causal inference. For example, in empirical real-world evidence study, it's usually unclear which of these missing data patterns and mechanisms are dominating, and especially how this relates to bias when we look at high-dimensional covariate spaces such as database linkages. And so as part of the FDA Sentinel Innovation Center work stream here, we aimed to develop like a principal approach so that people or researchers just do not just only assume missing at random mechanism and go on with their imputation and that's it, but that they have a way to characterize the missingness in a more structured way. And also to implement all of these and to streamline that as part of an R package. And we did this with some very comprehensive simulations at the development site where I work. So at Mass General Brigham, we used the EHRs here, deterministically linked them to claims data, and developed this kind of R package based on the theoretical work that we did with these simulations. And now we have shipped this toolkit to our testing site, which is at Duke University, and they are now testing our package on their EHR claims linkage. And just to give you a brief idea about the scientific and technical background of the R package, I just want to give you an idea of how we set up these simulations. So very basically, we assumed general missingness structures that we often see in electronic health records. This can be missingness mechanisms that are completely at random. So the missingness is completely independent of any observed or unobserved factors. So this is shown here in the causal diagram in A. In B would be a missing at random scenario where the missingness could be explained by fully observed covariates that we denoted here as C1. And then we also looked at two missing not at random mechanisms, because these are usually the ones that we are mostly scared about because they can introduce huge bias. And in C, this would be dependent on an unobserved factor that we do not have measured as part of our database. And in D, the missingness would solidly depend on the value of the partially observed covariate. And so we did some theoretical thinking and checked, can we not do any groups of diagnostics that can give us a little idea about what the missingness process could be here. And so group 1 diagnostics would compare the distributions of observed covariates between patients with and without an observed value of the partially observed confounder. And this can be then quantitatively expressed, for example, as the absolute standardized mean difference, where very analogous to propensity scores, if you're familiar with them, you would say an absolute standardized mean difference less than 10% would show no real imbalances in observed patient characteristics, and the missingness hence may be likely completely at random, or in a more drastic case, missing not at random, since we cannot really explain the missingness. And if it was 10% or higher, the imbalances in observed patient characteristics could lead us to the conclusion that the missingness may be likely at random, because we can observe or we can explain this observed missingness. And analogous to that, there's also like formal statistical tests according to Hodling and Little, which are basically multivariate t-tests or chi-square tests that give us a p-value for exactly this comparison. In group 2 diagnostics, what we did is we assessed the ability to predict the missingness of the partially observed confounder based on observed covariates. And with the resulting AUC, so how well we can predict the missingness, this could give us an idea about the underlying missingness mechanism, because if we can predict the missingness well, then we could probably also explain the missingness well based on observed covariates. And this would lead us to the direction of the missingness being at random. And then lastly, group 3 diagnostics checks whether confounder missingness is associated with the outcome. So do we have differential missingness between the two groups? And so if there's we thought that if there's no association in a univariate or nor in an adjusted model, we will probably not see meaningful differences in the estimate that we get even after full adjustment, and that would mean that we likely see missing completely at random mechanism. Whereas if we see an association in the univariate model but not in the fully adjusted model, this would rather lead us in the direction of a missing at random mechanism. And if we see meaningful differences in both univariate and adjusted model, this would be rather likely a missing not at random mechanism. And these are just the results of the plasmid simulations that we performed. And these kind of large-scale simulations kind of revealed that the assumptions were true that we made, and that the combination of all 3 group diagnostics, but only as a combination, gave us a better idea about the underlying EHR missingness structures. So how could you now use that in a reproducible fashion in your real-world evidence study? So given the benchmark that we set in the simulations, we thought that if we look into EHRs, we may be able to explain similar patterns that we see based on these 3 group diagnostics. And so, for example, here, the EGFR, which is a common cancer biomarker, for example, in non-small cell lung cancer, these kind of values, this battery of values in these group 3 diagnostics, pretty much map to what we observed in the simulation as the missing at random mechanism. And similarly, ECOG matched very well to what we observed as a missing completely at random mechanism. So I think you get the idea of what we're trying to do here. And so the SMDI package, SMDI stands for Structural Missing Data Investigations, now tries to streamline these 3 group diagnostics to approach missingness more structurally and in a more principled fashion. And the SMDI package, so this is basically the entire workflow that we thought of when we developed this R package. So you come with a data frame that has 1 row per patient and the relevant variables as columns. And the relevant variables are exposure, the outcome, the covariates, and of course also your partially observed covariates that you want to investigate. So the first step then would be to produce some descriptives and pattern diagnostics. Here are a couple of functions to do that. So you would start with just summarizing and describing the missingness and identifying the patterns visually, which can be, for example, be done with like set visualization techniques. Then you would go on to some inferential, to the inferential group diagnostics that we validated in our simulations, for which we then also have different functions that I want to walk you through right now. So if you want to download this package, it's available on CRAN, and it also comes with some bundled data sets that you can use to explore the functions of the package. SMDI data includes some already like pre-simulated partially observed covariates, and SMDI data complete is a complete simulated data set if you prefer to kind of introduce the missingness mechanisms yourself, and you can use those data sets to play around with. So first of all, this is just some very basic descriptives. It shows you the covariate, the count of missing observations, and the proportion of the missingness. So nothing too exciting here. Then in terms of the patterns, so something we wanted to do is to show or to be able be able to visualize the missingness patterns in a set visualization technique. And for that, we actually use re-exports of the Narnia package and the mice package, because they have two functions which are actually really great in visualizing these missing data patterns. And so we did not see the necessity to reinvent the wheel here. And so this is one example of how missing data patterns can be visualized. Now, more importantly than the group 1 diagnostic could be resampled using the smdi ASMD function, where you basically just define the data frame. If you want to compute the mean or the median of the absolute standardized mean difference, and this will then give you one value and the min and max per partially observed covariate. Now, this is just a print output. The resulting ASMD object will give you much more information than what is captured in the just generic print output. So it will give you a complete kind of table 1. So a contrast of what are the patient characteristics stratified by if the partially observed covariate had an observed value or not. And further, you can also visualize the absolute standardized mean difference for each of the partially observed covariates as part, for example, of here of this ggplot. Now, also in the group 1 diagnostics, I mentioned Hotterling's and Little's test. So this will also give you here the test diagnostics and the p-value. And the same also with Little. Little here is a bit different because it assumes that the missingness mechanism is defined globally. So even if you have multivariate missingness, and so you get just one p-value across your entire data set. Now for group 2 diagnostics, this will test the ability to predict the missingness, and the smdi RF function basically trains and fits a random forest model with the random forest R package as the underlying engine for you to assess the ability to predict the missingness for the specified covariates. And since random forest models, especially on large data sets, can be very time consuming to train and to run, we also implemented here parallelization. If you have multiple variables that are missing, with the end-course parameter, with which you can basically then parallelize across your partially observed covariates. And then the resulting output will not only give you the AUC, so how well you can predict the missingness, but it will also dive a bit deeper and tell you the covariate importance for the prediction that was being done. And this can also give you quite some hints on the potentially underlying missingness data generating mechanisms. For example, if you observe certain covariates which contributed very much to the prediction of the missingness. And then lastly, the smdi outcome then essentially just fits an outcome model with the partially observed covariate as a binary covariate in your computational model. And currently, 3 main types of regressions are supported, namely logistic for binary outcomes, linear for continuous outcomes, and the Cox proportional hazard regression for survival outcomes. And this just needs to be specified in the form left-hand side parameter. And you can also choose a couple of other parameters. For example, if you want to have the output exponentiated, and so on and so forth. And now really the flagship function that basically wraps all of the previous functions I've shown is the smdi diagnose function. And here you can, of course, then also take all of the parameters that you can specify in the single functions I've shown before, and the output here with a very most minimal example will give you an idea across all of the 3 group diagnostics and the little p-value. Moreover, the output, which is an object of type smdi, will give you the table and the p-value separately. And since I'm a big fan of the GT table package, there's also one more kind of styling function where you can basically take the output of this smdi diagnose function and pipe it into the smdi style GT, and it gives you a pre-formatted publication-ready GT table that you can then export to PDF, to Word, whatever you wanted, and send it along with your study documents, be it as part of a manuscript or something else. It also comes with some pre-formatted footnotes that give you an indication where the different test statistics came from, so group 1, 2, or 3 diagnostics, and of course also the abbreviations. Yeah, and as I mentioned, you can then use the GT save function to export it to whatever format is supported by this function. And with that, I want to thank you for your attention. And you can download the smdi package from CRAN. You can download the development version from our GitLab server. And please also go to the website that I've linked here, where you can find tons of more documentation, articles, and exemplary workflows that we produced with the simulated data that is part of the package.